Dear students, this is our fourth lecture in this series of polymers. And today in this lecture, we will discuss commercially important polymers. That what are their technique to manufacturing, what are their applications, and what are their important properties of different types of commercially important polymers. So first in the category of commercially important polymers is polyethylene, and we all know that polyethylene is a simple hydrocarbon polymer which was produced by ICI Industries, Imperial Chemical Industries in 1933 by polymerization of ethene. And this polymer can be synthesized either through free radical polymerization or by coordination polymerization. So the mechanism for free radical polymerization or coordination polymerization we have already discussed in our third lecture, that is the mechanisms in polymerization or polymerization reaction mechanism. Now, when this ethene is polymerized to give us polyethylene, depending upon the technique of polymerization used, that is free radical or coordination, we will get two types of polyethenes. One is low density polyethylene, which is known as LDPE, and other is high density polyethylene, which is called as HDPE. There are appreciable differences between the properties of these two polymers, LDP and HDP. For example, as far as melting point is concerned, LDP has a melting point of approximately 115 degrees centigrade, whereas HDP melts at about 135 degrees centigrade. So even on the basis of melting point, we can differentiate between low density and high density polyethylene. Then crystalline nature. The low density polyethylene LDPE has low crystallinity. So this is 50 to 60% crystalline. Whereas high density polyethylene is more than 90% crystalline. So on the basis of crystal structure also, we can differentiate between LDP and HDP. And here the main chain contains many side chains of 2 to 4 carbon atoms, and because of this this becomes a low density polyethylene, and amorphous nature is more as compared to crystalline nature because of these side chains. Whereas in case of HDP, they contain less than one side chain per 200 carbon atoms in the main chain. So basically this is a very linear chain polymer. So that is why it has a regular packing, and it has high crystallinity. Then flexibility, because this is having more side chains and amorphous in nature, that is why this is more flexible than HDP, because here the crystallinity in the polymer is low. Because of that, this is more flexible, whereas this is more rigid as compared to LDP because of the high crystallinity. Then strength, because this is less crystalline, so that it is not as strong as HDP, because here it has a regular packing of the polymeric chains due to high crystalline nature. Then heat resistance, it retains toughness and pliability over a wide temperature range, and but density drops off dramatically above room temperature because of these side chains, whereas this is useful even above 100 degrees centigrade. Then transparency, It shows good transparency as it is more amorphous than HDP. This is less transparent than LDP because of high crystallinity. Then density, as the name suggests, it has lower density than HDP of the range of 0.91 to 0.94 grams per centimeter cube, whereas this has a higher density as in comparison to LDP, 0.95 to 0.97 grams per centimeter. Then chemical properties is concerned, both are inert, uh, but in case of low density polyethylene, this is chemically inert at room temperature in most of the solvents, but as we expose it to light and oxygen, it loses strength and tear resistance also. Whereas high density polyethylene, it remains chemically inert. Then applications or uses in case of LDP, this is used in sandwich bags, cling wraps, car covers, bottles, liners for tanks and ponds, then moisture batteries in construction. Whereas high density polyethylene, this is used for freezer bags, water pipes, wires and cable insulation, and intrusion coating also. So this has more refined applications, whereas LDP is having more general applications. Then next commercially important polymer is polyacrylonitrile, or this is also called as PAN, polyacrylonitrile. This is formed from acrylonitrile or vinyl cyanide by free radical polymerization. So this type of polymer is formed by free radical polymerization of this carbon-carbon double bond, which first gave us a free radical from this monomer on reaction with free radical initiator, and then that free radical changes into macro free radical, and then termination takes place to give us this saturated polymer, which is called as polyacrylonitrile. So polyacrylonitrile is used in very few products except for making another polymer, that is carbon fiber. Then homopolymers of polyacrylonitriles, they have been used as fibers in hot gas filtration systems, outdoor awnings, uh, then sails for yachts, and even fiber reinforced concrete also this has been used. The next in the category is ABS. ABS, A means acrylonitrile, B means butadiene, and S means styrene. So basically this is a copolymer of these three monomers, acrylonitrile, butadiene, and styrene. So that is why this is popularly called as ABS polymer. The synthesis is complicated. Here we polymerize styrene and acrylonitrile. Uh, when this acrylonitrile and styrene, they will polymerize, we will get this type of polymer, which is called as SAN. S is for styrene, AN is for acrylonitrile. So this is styrene uh, polymer, and this is acrylonitrile. So when they condense with each other through addition mechanism, then we will get this type of polystyrene acrylonitrile. So styrene acrylonitrile copolymer SAN is formed. Then this SAN reacts with polybutadiene. So these two monomers, they are reacted in presence of polybutadiene, and we will get this type of polymer, which is called as ABS polymer. So what happens is, on this chain of polybutadiene backbone, we will have the chains of SAN polymer grafted on this chain. So this has a complicated structure. This is you can say a grafting copolymer of acrylonitrile, butadiene and styrene. So first polymerization of these two will give us SAN, and this SAN will be grafted on polybutadiene backbone to give us ABS copolymer. Then this is a stronger plastic than polystyrene because of the presence of nitrile groups on the acrylonitrile, because we know that nitrile group is a polar group, and because of this the monomers, they are attracted to each other, and this allows opposite charge of the nitrile group to stabilize each other, and because of this attraction between the opposite charges, the polymer becomes very strong. Then strong attraction holds ABS chains together tightly and makes the material very strong. The uses This is used in lightweight automobile body parts manufacture. Then it is used for manufacturing of plumbing pipes, structural panels, kettle handles and housewares. They are also manufactured from ABS plastic. Then next very common and very important polymer is polystyrene. And as we have seen that polystyrene is formed from free radical polymerization of styrene, and we have seen the mechanism of formation of polystyrene in the earlier lectures also. And this styrene monomer is itself manufactured in industry from benzene by reaction with ethene at 600 degrees centigrade in presence of aluminum oxide. So when these two, they are reacted at this high temperature in presence of aluminum oxide, they are converted into styrene, and this styrene in presence of benzoyl peroxide as free radical initiator, or AIBN as a bis isobutyronitride as free radical initiator, is converted into polystyrene through free radical polymerization. The advantages of this polymer is that this polymer is a very cheap, rigid and transparent polymer, and this can be easily molded and has good dimensional stability. Then it has good electrical properties also. Then low dielectric loss, and it shows excellent resistance to radiation, particularly gamma radiations. But it has some disadvantages also. Disadvantage is that it is very brittle, and it is affected by organic solvents, so this shows poor chemical resistance to the organic compounds. Then it is degraded by UV light also, and it is flammable also. You can say it is highly flammable. So these are a few of the disadvantages of polystyrene, but this is commonly used because this is a very cheap material. Then we have seen a number of applications of polystyrene. This is used as an extended polystyrene under the name styrofoam, where 5% polystyrene is mixed with 95% air, and very lightweight material is formed. And this lightweight material we have used many times in the form of tea cups or coffee cups and takeaway food containers. Then this polystyrene is also used as an insulation in building structures, and this is also used as packing material inside the boxes. Whenever say we have purchase some item, say computer or laptop, you must have seen that there are some material, white colored material, very lightweight, that is polystyrene, which gives cushioning inside the boxes. And then this is also used in architecture models also. So, as you seen that the polystyrene is used in our home, office, local grocery shops, cafeteria, everywhere there is a use of polystyrene polymer. Then this is also used in plastic model assembly kits, plastic cutlery, and many other objects. They are made from polystyrene. So this is very commonly used, and it is a economically very cheap to have much more applications in spite of its disadvantages. Then next is polyvinyl chloride. Polyvinyl chloride is also known as vinyl, and this is synthesized by the polymerization of vinyl chloride. And here also this PVC or polyvinyl chloride is synthesized by free radical polymerization. That means vinyl chloride in presence of some free radical initiator like organic peroxide or AIBN as a isobutyronitrile will lead to the formation of polyvinyl chloride. And this vinyl chloride itself can be synthesized from these two methods, either by reaction of acetylene in the presence of HCl gas at 150 degree centigrade in presence of some metallic catalyst is converted into vinyl chloride, or reaction of ethylene dichloride. This undergo dehydrohalogenation at high temperature and pressure. So pressure of the order of 25 to 30 atmospheres and temperature of the order of 550 to 650 degree centigrade. So dehydrohalogenation will take place and we will get vinyl chloride as the product. Whereas this reaction is an addition reaction, this reaction is a dehydrohalogenation reaction. But both of these reaction, they will give us the monomer vinyl chloride, which can undergo free radical polymerization to give us polyvinyl chloride. So this is how we can manufacture polyvinyl chloride or vinyl from vinyl chloride. The properties of PVC, it is resistant to water, acid, bases, then some organic solvents, fats and oils. So that means these many type of molecules, they do not affect this polyvinyl chloride, and it can be heat sealed between 90 to 180 degrees centigrade. This is colorless, rigid, and it has a low softening point. It has a higher density because this is a long chain polymer, and the high chlorine content of PVC makes it nearly inflammable. That is, this is less flammable as compared to other polymers where we are not having the chlorine or any other such type of atom present. Then GTT, that is glass transition temperature, is 50 to 60 degrees centigrade, and because of that this cannot be used for hot water pipes, but this can be used for cold water pipes. This is attacked by strong oxidizing agents. So the applications where we are using strong oxidizing agents, there we cannot use PVC. And common applications is PVC used in manufacture of bottles, window frames, pipes, flooring, wallpaper, toys, car seats, guttering, cable insulation, credit cards, then medical products such as blood bags, they are also synthesized from polyvinyl chloride. In addition to above application, this is also used in manufacture of food containers, molded articles and water pipes. The next category of commercially important polymers is polyesters. And we know all our synthetic fiber from which our clothing is made, this is mostly made of polyesters. And these are formed by condensation polymerization, and normally polyesters, they are formed from the condensation of dicarboxylic acids with diols. So for example, this is how PET is formed, polyethylene terephthalate. When terephthalic acid 1,4-benzene dicarboxylic acid is reacted with ethylene glycol, then H from here, OH from here is eliminated, water is removed, and we know that if a small molecule like water or HCl or ammonia is removed by the condensation of the monomers to form a polymer, then such type of process is called as condensation polymerization. So because here we are removing small molecule like water, so that means this polymer is being made by condensation polymerization. And if in the polymer we are having this type of linkage present, this is an ester linkage. So polymer which is having this type of linkage is called as polyester. So dicarboxylic acid condensing with the diol, giving us polyester as the product, and this is popularly known as PET, polyethylene terephthalate. And PET is used for clothing. We say terylene and dacron fibers, they are polyesters. Then home furnishing and textile cord, they are made. This is also used in manufacture of safety helmets, aircraft battery boxes. Then anti-greasing and wrinkle resistance clothes, they are also made of polyesters. Then these are some of the common methods by which polyesters they are made. So we can use diphenols also instead of alcohols. So diphenols, again OH group on this side and OH group on this side. So when they will condense with dicarboxylic acid, again elimination of water molecule will take place like this, and these are having this type of ester linkage. And because this is having an ester linkage, so this is an example of polyester. Then polyesters can also be formed from the condensation of anhydrides with glycols. So here we will get three-dimensional polyesters. So when 1 mole of this will attack this carbonyl to open this carbon oxygen bond, then one chain will be formed on this side, then O negative, this will condense with another molecule of ethylene glycol, one chain of polyester will be formed on this side. So we will get three-dimensional polyesters like this by condensation of phthalic anhydride with ethylene glycol. So in general we can say the condensation of dicarboxylic acids with diols. Dicarboxylic esters can also be used. So here when esters they are used with diols, then we will be seeing the elimination of alcohol instead of water. So here two molecules of alcohols they will be removed to give us polyesters as the product. Similarly, we can use carboxylic acid derivatives also. So dicarboxylic acid chloride, so acid chloride on this side, acid chloride on this side, they can condense with the diols. So H from here, Cl from here, HCl is removed. H from here, Cl from here, HCl is removed. So two molecules of HCl, they are removed by condensation of one molecule of this and one molecule of this to give us one molecule of this polymer. So when n number of the monomers they condense, we will get a polyester of this type. So these are some of the common monomers which can be used for the synthesis of different types of polyesters. Then some more three-dimensional polyesters, they can be formed like this. This is a glyptal polyester. So anhydride on reaction with triols. Instead of glycols or diols, we use triols. When triols are used, then we will get a three-dimensional structure of this type in the form of polyester. And such type of polyesters, they are called as glyptal polyesters. So in addition to this, we can use dianhydrides, then triols, tetraols. They can also be used as monomers, and we can have different types of glyptal polyesters as the product. Then next is polyurethanes. Polyurethanes are also very well-known polymers, and that kind of foams which are formed by these types of polymers, and you must have seen the use of these polymers in refrigerators. The foam which is present in refrigerator is formed of polyurethanes. So these are single most versatile family of polymers which can be used as elastomers also, paints also, fibers also, and adhesives also. And this is because of a specific linkage which is called as urethane linkage. So when we are having nitrogen and oxygen on the two sides of a carbonyl group, then such type of linkage is called as urethane linkage. Or you can say the amide linkage, if is extended by an oxygen linkage, then this is called as urethane linkage. So if we see two things, this is an amide linkage and this is an ester linkage. So together they form urethane linkage. And polyurethanes, they can be synthesized from diisocyanates. So this is isocyanate group. This is present on both the sides of the molecule. So diisocyanates, they react with glycols, and this H, this oxygen will attack this carbon, and this carbon nitrogen bond will become a single bond, and this hydrogen will be transferred to this nitrogen on one side. Then another molecule of ethylene glycol that will react on this side, and that is how we will get a polymer of this type, polyurethane. And this linkage, as I told you, is called as urethane linkage. So any polymer where this linkage is present, urethane linkage, will be called as polyurethane polymer. Then is epoxy resins. Epoxy resins, they are formed by the polymerization of bisphenols with epichlorohydrates. So epichlorohydrin is this three-membered oxygen containing heterocyclic compound having chlorine on the beta carbon. Alpha carbon to the ring. Now when these are condensed with each other, H from here, Cl from here will be removed to form oxygen carbon bond. So oxygen carbon bond will be formed. That means one bond will be an ether bond, ether linkage will be formed. Then another way is that the oxygen can attack this carbon, and this can open to give us OH group, and then this OH group can further react with another molecule of epichlorohydrin or this one, and we can get a polymer. So these types of ether linkage containing polymers, they are called as epoxy resins. And when this is a long chain, single chain polymers, then these OH groups formed by opening of this bond, they may be free also. So these ether linkage and free OH groups, this gives a very flexible structure to these types of resins, which are called as epoxy resins. And due to the presence of these ether linkages, these polymers, they are very stable, and because of that they have high resistance to water. So they are hydrophobic in nature. Then they are not affected by organic solvents or acids or alkalis or other chemicals also. So because of this ether linkage and then OH group present, they are polar in nature also. Then like I have told you, other reactive groups, epoxide and hydroxyl groups, they are widely spaced. So because of the higher range of space, they are highly flexible materials. Then because of the cross linking, they are tough also, heat resistance also, they show heat resistance also. So polar nature of these molecules, they give us very excellent adhesion quality, so that is why they are used as adhesives also, epoxy resins. So some of the important applications of epoxy resins, they are used as surface coatings. Then as I have told you, they are used as adhesive. For example, araldite, which we have used many times, is a epoxy resin. Then they are used as glass fiber reinforced plastics also. Then they are used for materials for skid resistant surface on highway, that is coated with epoxy resins so that the vehicles, they may not skid. Then they are used for production of components of aircrafts and automobiles. Then cotton, rayon and bleached fibers, they are coated with these epoxy resins so that they can have crease resistance and shrinkage control. So cloth will not shrink if we have coated this with the epoxy resins. Then they have been used as laminating materials also, and also they have been used in manufacture of electrical equipments. So this is the book which has been used to prepare this lecture, Chemistry for Engineers by Harish Chopra and Anupama Parmar. This book has been published by Alpha Science UK, and national edition of this book has been published by Narosa, Delhi. Thank you very much for patience hearing.